So welcome everyone to MD&A's Parts Division Guardian and Vortex Shutter Design Installation Process and Benefits webinar. Just wanted to say welcome and thank you for joining. Just so you know, at the top there are features where there's the Q&A as well as the chat feature. I wanted to let you know that the chat feature is currently disabled. So if you do have any questions, you can put them into that Q&A. If you click on it at the top, it'll pop up on the right side there, and you can enter your questions, create a post, and it will send it to us for any of your questions. And just so you know, we'll be answering all the questions at the end with Jacques. So take it away, Jacques. Thank you so much.
I'm senior seals engineer for the MD&A Parts Division. I design various types of packing and seals, including the Guardian and Vortex Shutter product line that we have patented and exclusively make here at MD&A Parts Division. I'd like to just go through the design process, the installation process, and the benefits of using Guardian Vortex seal technology. First of all, just a brief discussion for familiarization for people who may not be intimately familiar with these parts. We're talking about the seals within the steam turbine system specifically. Those seals are designed to contain steam within the turbine areas where the steam can, perform work, give energy, or to keep air out. And the seal rings are the active components of those sealing systems. There are other components we're not discussing here. Just in terms of how types of seals we're talking about typically work, seals they function primarily by providing a series of throttlings or pressure drops to minimize seal leakage, between a rotating shaft and a stationary component. That is usually using sharp orifice teeth, although there are other technologies that perform the same purpose. When using sharp orifice teeth, small space between the rotating shaft and stationary seal provides a non-contact interface. In other words, you don't have the seal teeth rubbing on the rotor. Spill strips are basically what we call the seals that go over the tips of the buckets or blades that provide work. They basically function in the same fashion as the shaft seals. Again, they're usually using sharp teeth, and the small space between the seal surface and the stationary teeth provides a non-contact interface. And then just a discussion about Guardian Vortex Shutter technology and how it may differ from conventional seals, I guess you call it. First of all, the main problem that we're trying to resolve in design of seal strips and packing rings for seals is that steam that bypasses the steam path, the blades within the turbine does not do work. In other words, it's just essentially thrown away. So what we do in order to provide benefit to the sealing system is we have a technology called Guardian, which works on the bore seals to maintain sharp teeth at the bores of the stationary components, and the Vortex shutters provide a benefit at the tips of the buckets for rotating components. Just a note, shaft and tip seals or leakage is approximately 1/3 of the stage efficiency loss that you might see from outage to outage. So it is significant. The Guardian rotor seal minimizes wear by providing sacrificial strips in place of two of the normal sharp teeth. And we'll discuss in a few minutes how those sacrificial strips work to keep the other teeth sharp, which is why they're the Vortex shutter tip seal uses certain differential velocity interfacing with axial disturbances in the seal tube to create a low pressure zone upstream of the seal tube. And we'll discuss how that works as well. Mutual benefits of the Guardian Vortex seal technology. They're always manufactured from stainless steel for longer life. They are in-kind replacements for conventional seals. You do not need to modify your other components in order to use Guardian Vortex technology. For the most part, there are exceptions. It provides a longer seal life with higher efficiency than get to conventional seals. That longer seal life retains unit heat rate between outage intervals, basically for a longer period of time than conventional seals would do so, and combined, they're proven to increase overall turbine efficiency. In other words, if you use both Guardian packing and vortex shetter seal technology, it is proven to increase unit efficiency above design by 1.5 to 4.5%. And we have a few case studies at the end of this presentation where we'll discuss that. First of all, we'll talk about the Guardian packing range for seals. The seals operating at the bore of, say, like an impulse or a low to medium reaction diaphragm. During normal operation, it operates as a seal. There's a clearance between the teeth, whether they be Guardian guard posts or the sharp teeth, and basically the Guardian posts in this operational scenario are basically just ready to provide protection as necessary. There's a spring on the Guardian packing that maintains the radial position of the packing and maintains the gap between the seal teeth and the Guardian. In this scenario, during normal operation, does not. If there's a condition where rotor comes closer to the stationary seal than it's desirable or it's designed for, what happens is the Guardian posts basically interface with the rotor and push the seal ring away from the rotor. That maintains the sharpness of the remainder of the seal teeth. That works because the Guardian tooth is actually slightly longer than the seal teeth. It is 5 mils or 5 thousandths of an inch closer to the rotor than the sharp seal teeth. So if the rotor moves closer to the seal, then the Guardian post interface of the rotor moves the seal away from the rotor and maintains the seal tooth sharpness. They're relatively simple technology, innovative enough where it's actually happening. The vortex shetter is, again, operates over the blade tips. That uses a different technology. Essentially, the vortex shetter is installed on the upstream of the tip seal. The shape and the spacing of the vortex shetter is optimized for each design based on standard rules that we've learned over the years. Essentially, what happens is the vortex shetter shape is like a wave almost in the seal tube, and that is spaced at certain intervals around the circumference of the seal. That protuberance interfaces with certain potential velocity that is naturally occurring within the steam path and creates a high pressure or a low pressure spot, basically, just upstream of the first seal tube. And that low pressure region reduces the pressure drop across the seal tube, which reduces the flow across the seal tube, resulting in lower flow, lower loss, and improved efficiency. And then, in order to implement Guardian and Vortex seal technology in a specific turbine, we have what's called a pre-measurement. What we do is, especially for a unit where we have not done seal work in the past or have not measured for Guardian Vortex seal technology, we schedule a time early in the unit outage to measure the various components of the turbine that will interface with the seal to ensure that when we design the seal and manufacture it, that it will be able to be dropped in the turbine with a minimum of additional effort. So what does the pre-measure process look like? We're trying to define or quantify the critical parameters required to retrofit Guardian packing or vortex shetter spills. What we do when we do that is we reverse this packing or the spill strips. Sometimes we don't necessarily have to do that because we know them by part number, but a lot of the time we do actually reverse engineer the existing seals within the turbine to ensure that when we produce replacements that they will drop in with them. We measure the rotor diameters, band spacing, interfaces, things of that nature. stator or packing holder diaphragm measurements, measuring again interface diameters, any other concerning factors like dishing, distortion, things like that. Through the design process, we'll figure out what we're going to do about those sorts of factors that are outside of design. We obtained the OEM design radial and axial clearances. It's important for us that combines with knowing the opening radial clearances, the clearances that were present when the unit was opened up for outage, and any closing clearances from prior outages. All those factors are used to determine optimal clearances for seals going into your turbine for the next outage or for the outage that's currently going on. The reason that is important is there are many instances where the original equipment manufacturer radial clearances specifically, but sometimes axial clearances are not the best fit for specific turbine. We've come across a lot of turbines with OEM design clearances with excessive radial rubs, sometimes excessive axial rubs. We try to avoid those scenarios when redesigning seals. So the best way to do that is basically look at what clearances look like when your unit opened up, take a look at the OEM clearances, and figure out if there's an issue that we resolve, during the seal design process. And as part of that, we also look at sometimes, you might have excessive rubs during, from, the last outage to your current outage, but it wasn't necessarily seal design or the OEM clearance, seal clearance design, but it's because of, say, a poor alignment or some alignment issue going on. So we try to weed that out. And the pre-measure basically, again, ensures that guardian packing vortex shutter spills can be installed with minimal additional time required. So basically, the design clearances, just discuss, the various things that we're talking about in a little more detail. Often a clearance drawing will show like a cross section, and it'll have various values for, say, the axial radial clearances between bucket tip seals and the bucket, and between the diaphragm bore seals and the rotor. So those we basically take all those numbers and put them together, and I'll usually post-process them into a nice little visually representative presentation of what the opening and closing clearances. So these are recorded in different ways, but they're usually in ways similar to this. Essentially, you have people on site that measure when the unit opens up, the different, the location of the various rotor seals and tip seals between the seal teeth and the sealing surface, and opening clearances when it's opened up, and closing clearances. For the purposes of our discussion, opening clearances are actually a little more important, but closing clearances are also important because sometimes rub conditions, you don't always replace seals every outage. Sometimes rub conditions occurred in a prior outage and were corrected, and it's important for us to try to weed that out when we're doing our clearance analysis. So as part of the design process, I usually will go through the opening and closing clearances and the OEM clearances, and I'll figure out what we want to use for radial design clearances on our specific seal design. Any changes to axial design clearances, rotor diameters for interfaces, hook diameters for interfaces, seal dimensions, other diameters, basically the tooth locations within a seal, things like that. And we have usually there's depending on the OEM design, there are other design features of the OEM that we prefer to apply our guardian vortex design. So basically, we start out with radial clearances. So again, what I usually do with the data collected earlier is I will put it together in a chart and compare it to the OEM clearances with the eye of, are the OEM clearances sufficient for us to apply for this, this current outage, these new seals, or do they require some sort of tweak? The OEM clearances sometimes are not correct for for a specific turbine or power plant. There are times when the OEM clearances, usually they're too tight, result in excessive rubbing, which results in lost performance and issues with operability. Occasionally, they're actually too large. If we see large, perhaps we'll discuss whether we want to tighten them up or if there's a reason why they were increased. Or as a rough seal tooth flows 25% more steam from a sharp seal tooth, we're trying to set radial clearances to minimize tooth rubs, but and that would want you to increase clearances. However, we want them to be as small as possible to minimize seal leakage. So it's kind of a balance. With axial clearances, essentially what we're doing, we're comparing them to the OEM clearances again, and basically trying to determine if there, first of all, if during opening there were issues with axial rubs, say for example, something similar to the picture below where the seal teeth are bent over sideways because the rotor traveled too far and basically pushed the seal teeth over. Was that because the axial clearances are set incorrectly in the previous outage? Is it because there was a design issue with the axial clearances from the OEM? Is it because there was some sort of operational issue that caused, say, a long rotor, short rotor condition that resulted in that rub? We try to weed all that out as part of the design process. But again, essentially, we don't typically modify axials unless we see a significant problem. But if there is a significant problem, we try to figure out where that problem is coming from so that we can proceed forward with the best axial clearance design for the new seals. In terms of defining rotor diameters, measure all the rotor diameters, we measure all the interface diameters. So we measure the low land and high land and the spacing between the lands. That's self-explanatory. In terms of the seal holders, usually most packing rings and tip seals interface with, if they're movable seals, then they interface with a hook fit. They fit into a hook fit. We measure that, measure basically usually horizontal, vertical, sometimes some others, basically trying to determine, well, first of all, what the actual interface diameter is. Second of all, if there's any distortion in that interface diameter, and if there is distortion, if it's going to be done to address that, either by us in the design of the seals or in terms of, say, our repairs division in terms of repairing something that's rerounding. It's usually what it's called. And then also reverse engineer the seals, as we discussed earlier. Reverse engineering essentially is defined as capturing because these seals are around a shaft. They're typically a round seal, so you have a cross section and then you have other features that are unique depending on where you are in circumference. So first of all, we'll define the cross section. Basically the interface with both the stationary and rotating component, the tooth spacing, things of that nature. Obviously, if there's axial clearance issues that we need to disposition by shifting the seal teeth in one direction or the other, we'll figure that out as well. One of the modifications that we made to seal designs is many OEM seals are sprung much too stiffly. They do not take advantage of the pressure of the steam pushing the seal outwards towards the fit. As part of that, and for compliance reasons for the Guardian seal, we actually convert the spring design of the OEM to a coil spring. Now, some of the OEMs actually do use coil springs. However, some say, for example, a General Electric uses like a flat leaf spring. Coil springs have several benefits other than providing a compliant fit with the seal. However, I'm not really going to discuss those here. We can ask about those later. Basically, it has to do with stress distribution on the spring material itself. I'll just leave it at that. And then after we've designed the seal, we go deciding on what clearances or any changes in clearances required for a specific turbine. So then we go through how our on-site seals division actually performs the seal installation. And why is it necessary to custom fit packing and spill strips? We do our best when we're measuring various components. However, there is distortion and things of that nature that we can't necessarily capture adequately during the seal design. So one of the things that the OSS seals team is trained to do is to look at the seals as they're going in and point out any issues and correct them before the unit goes online. That's we obviously want to make sure that before the unit goes online, the seal design is something that is not going to cause any problems of any nature. One of the other things that they can do, they can actually fine tune the radial clearances, which helps improve unit efficiency. Basically, again, making sure that we obtain optimum radial clearances. Various things that might, require more work as part of the custom seal installation. Again, we're talking about holder distortion. If it's out of round, if the holder horizontal joints are stepped, in other words, if one half of the holder has seal base further upstream than the other, so that the two halves of the seal are actually in different axial configurations. A dish diaphragm may or may not require on-site adjusting, depending on whether we dealt with it, either again by repairing the dishing or by capturing how much dishing there was ahead of time and shifting the seal to compensate for that. Misalignment of holders, sometimes we design for an optimal alignment situation, but for some reason, say you have like a long N2 packing head, you kind of, when we're designing the seals, we kind of design for the optimal center line distribution. However, because of the rotor configuration within that holder, sometimes it's not optimal. That's something that OSS can design or adjust for, basically by trimming hooks, shift the center of individual seal rings, left or right or overhead, if necessary. And also sometimes components are modified between when we capture dimensions and when they get reinstalled on site. Maybe you have a change to a rotor diameter. It's fairly rare. Bucket replacements. Sometimes buckets are replaced, cover diameters change slightly, so they'll be able to fine tune that. Diaphragm repairs, those are the kind of things that OSS can handle on site with their machining technology. So part of the installation process, the first thing they do is they ship a portable machine shop to site. That portable machine shop is basically a container with a mill that allows them to individually mill segments to fine tune them to the factors we discussed earlier. Technicians are mobilized. Those guys that go out there and actually work. They go out there and they unbox and inventory the packing, spill strips, and springs, make sure everything is there that they need to perform their job. They install the seals. They measure butt clearance and bore diameter of each seal. They will compare the bore diameter to what they need for clearances. The butt clearance is essentially a required differential seal ring and the holder. The required butt clearance changes slightly depending on temperature and material you'll use. However, they will deal with that on site. They mark or scribe retaining pin slot locations. Usually we machine for seal keys in the factory. However, because the retaining pins for circumferential movement, they move a lot depending on the OEM and whether they're in the same hole as they were previously, where the new holes are drilled. Those are done on site. We talked about butt clearance. They will calculate based on measuring bore diameters and the rotor diameter, rotor location, what they need to do in regards to radial clearances. They'll do that. They'll machine for that retaining pin slot, install the seals back after they're done machining. After the rotor gets dropped back in, they'll measure the radial and axial clearances. They'll discuss that clearance data, the radial and axial clearances with the field engineer and or the customer. in other words, just making sure that everyone's comfortable with the final design clearances in case anything else wants to be adjusted. Hopefully not, but in the event that there's significant consternation, they are there to be able to adjust components as necessary to address issues, and that they demob and go on their merry way. Then we'll talk about some case studies. These case studies are basically examples of the benefits that Guardian and Vortex technology has provided to different customers over time, both with regards to performance improvements and also wear reduction, as you say, or sustained improved radio clearances. So just again, start out with an operational history overview. We are probably close to 400 units globally in terms of units that are operating with Guardian Vortex Seal technology. We've installed it in basically all the large steam Schenectady units, medium steam, which used to be Lin units, and then transition Schenectady. We do have one or two, well, at least one or two Fitchburg size units. We've done it in Westinghouse units, both impulse and reaction design. We've done it in Hitachi, Siemens, also making the Toshiba, GC Parsons, Alice Chalmers, LMZ, which is a Russian manufacturer, Dresser-Rand, Bilibal. There's probably some I'm missing, but yes, we've applied Guardian Vortex Seal technology across many different OEMs. I'm not saying that it can be installed everywhere, but we know what we need to do to install it in a specific unit and whether it's a possibility. That's part of the review process when we quote Guardian Vortex Seals, is whether we can do it or not. Just discuss one specific case. This is a case where Guardian Vortex Seals were installed in a HPIT of a D11 steam turbine, 1050 F inlet, 1800 PSI, nominally a 200 megawatt steam turbine. Essentially, what happened was there was a third-party steam path audit that calculated an expected efficiency gain, replacing the existing seals with a new conventional or OEM seal design. And instead, the customer elected to go with Guardian Vortex Seal technology. What afterwards, there was the customer measured the seal, the efficiency of their HV section, after Guardian Vortex Seals were installed. And essentially, the initial estimate for OEM seal, if OEM performance improvement, or OEM seals installed performance improvement was 2.1%. The measured with Guardian Vortex Seal technology was 3.5. So that is an incremental improvement in efficiency for a section of 1.4%. So again, with a combination of Guardian Vortex Seal technology, there is a demonstrated and measurable performance improvement on a section efficiency basis. Here's another example. This is Guardian and Vortex installed again in an HPIT. This is a Toshiba steam turbine, very similar to a GE steam turbine. There are some differences, specifically tip seal design. Nominally 200 megawatts, similar size to the D11 we were discussing earlier. Again, there was, in this case, it was MD&A who performed the steam path audit. They came up and they said, your HP efficiency improvement, if you go back with the conventional seals, would be 1.9%. The customer elected to have us put in Guardian Vortex Seal technology. They realized a gain of 2.8%, so that resulted in improvement for them of 0.9% in your HVIT section. Again, real benefit, real measured benefit for a section efficiency. This is kind of a different take on benefit of Guardian Vortex Seal technology. Essentially, this is these are measured clearances on 600 megawatt class steam turbines. So you're talking like a big like G series, for example, GE steam turbine. Essentially, what you have is at the bottom, you have what the dotted lines, like the lowest dotted straight line, the black line, that is the design clearance that we designed the Guardian seal to. The gray dotted line is what we left the seal to after design. So, after the installation team has gone through and done their installation work, that's what the actual as measured clearances ended up being. Then there was, the turbine operates for a period of time, and then it's opened up after outage. The blue line is indicative of how the Guardian seals would look like after, say, like a 10-year operational interval. Guardian seals, unfortunately, don't zero wear. However, they are much more resistant to wear than the OEM seal designs. The other two lines above, the brown and the kind of like peach line, those are units without Guardian seal technology, and those are the types of radial clearances you might see in a unit without Guardian seal technology. So you can see the difference between the line and the brown and the peach line essentially indicate that there's significant improvement in the expected wear of seals between conventional OEM seal design and Guardian seal design. This is a similar chart for an LP. In this case, it's actually the same turbine. Again, you have the black dotted line at the bottom, which is the design clearance. Gray dotted line is the as installed clearance. That turbine operated for a period of time and has radial clearances that is represented by the blue line. The brown line in this case was basically the clearances that they had prior to the outage of the installed Guardian design. And you can see there's a significant improvement between the clearances from the previous outage, which was in 2006, and what they found in 2015 after operating for almost 10 years with Guardian seals. So these are, again, measured, proven performance or performance improvements, seal improvements from the OEM design. And that's actually all I have.